Good morning, good afternoon, whatever. We're going to start with differentiation. Today there's only really a couple of sections in this chapter here, and it's pretty formulaic. So today we're going to look at parametric differentiation. So that is when you've got your parametric equations and you have to find the derivative of the Cartesian from the parametric equations. And basically, we can just use a simple rule, because if we start with the parametric equations, from the first equation, I can find dx over dt if I just differentiate this equation relative to t, and from the second one, I can find dy over dt. And basically, once I've got that and that, all I need to do is divide that one by that one. So if I write dy over dt divided by dx over dt, what I get is dy over dx, because the dt's will cancel each other out. So basically that's it. To summarize, you differentiate x relative to t, you differentiate y relative to t, and you divide the derivative of y by the derivative of x, and that's it. And your final expression would be as a function of the parameter t, but that's it, that's fine. So, a couple of examples just to see it a bit more clearly. I've got parametric equations x equals t cubed plus t, and y equals t squared plus 1, and apparently t is defined for all real values, and they ask me to find the gradient of the curve at t equals 2. So I want to find the gradient at t equals 2, and remember, in order to find the gradient function, we have to differentiate the function, right? So if I find dx over dt, what I get is 3t squared. If I find dy over dt, what I get is 2t. And then to find dy over dx, finally, dy over dx is just going to be 2t divided by 3t squared, which is 2 over 3t. And then, because I wanted to find the gradient where t equals 2, substitute in there, and I get 2 divided by 6, which is 1/3. So the gradient where t equals 2, just substitute it in there, and I just get 1/3. And that is it for now. That's just one example. I'm going to erase these and do another example and take it from there. Okay, so here we've got example number 2, where they're asking me to find the normal at the point P where theta is pi over 6, and the parametric equations are given by x equals 3 sine theta and y equals 5 cos theta. So again, I need to find the gradient function, because now I need to find the normal. So same idea. Dx over d theta this time, not t, is going to be 3 cos theta, and the y over d theta is going to be minus 5 sine theta. Derivative of sine is, the cos is minus sine, I think that's right, okay, good. And then dy over dx is going to be that divided by that, so that's going to be minus 5/3 of tan theta. So that's my gradient function. I need to evaluate the gradient where where theta is pi over 6. Now pi over 6 is 30 degrees. Where is my calculator? I'm using it as a prop for my iPad, so I'm going to have to work this out manually. So I know that the sine of 30, or the sine of pi over 6, is 1/2, and the cos of pi over 6 is going to be √3/2. So the tan is 1/2 divided by √3/2. So it's 1/√3. Okay, so we're substituting there. So the gradient m at theta equals pi over 6 is going to be -5/3. 5/3√3. Okay, cool. Which I could rationalize. But anyway, okay. If we remember now, the gradient of the normal is the negative reciprocal of that. So the gradient of the perpendicular is going to be 3√3/5. So that's the gradient I am looking for. The equation of the normal is going to be in the form y equals mx plus c. I've got my m. I need to find the c. In order to find c, I need a point. The point I know is where theta equals pi over 6. And if I substitute it into the two parametrics, I will get my y and my x value to find c. So, y is 5 cos theta. Cos theta is √3/2. So I get that the y value, 5 √3/2, is going to equal the gradient 3√3/5 times my x value, which is 3/2, plus c. That's a bit of a mess, but there you go. I've almost got my c there. What am I going to do? Put it all with a common denominator. I mean, you could use the calculator. I just haven't got it, so I have to do it manually. I want everything out of 10, don't I? So this is going to be 25 √3/10 equals 9 √3/10 plus 10c/10. So I can cross out the denominators there, take that to the other side, and then divide by 10. 25 take away 9 is 16 √3, so c equals 16 √3/10, which is 8 √3/5, because it can be simplified. So the equation of the normal that I'm looking for is y equals the gradient 3 √3/5 x plus 8 √3/5, my final answer. And I suppose that if they actually asked me to give it in a certain way, I could multiply both sides by 5 or do something like that. But anyway, so there you go, 2 examples on how to use parametric differentiation to find equations of normals and tangents. As you can see, it's not overly complicated. I believe you've got this sorted, and that covers the first part of chapter 6, differentiation. The next bit is a little bit trickier, okay, but we'll leave that for later on in the week. Have fun. Let me know if you've got any questions. Hope you enjoyed it. Like, subscribe, whatever. See you. Bye.